This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Okay, so welcome to the fourth lecture in this video, and before we go ahead and understand the other components of Gauss's law, what I would like to tell you a little bit about double integrals. Now, why I'm taking a step back, because these concepts, even if you know or if you don't know, you can just look into this video, which will give you a one-time solution to all the problems. So this first lecture was on the history, the second we learned on what is called the components, the third was electric field, and here we are going to catch up with few concepts, but we just look back into double integrals. Now, when we talk of a single variable integral, I mean to say a single variable definite integral in calculus, then in calculus a single variable definite integral is given by this, which you all know, obviously for f of x greater than equals to 0, and it is the area which we called under the curve f of x from xa to xb. Now, this definite integral can be extended to functions of more than one variable. So considering this kind of a variable z equal to f of x y, we call the definite integral is denoted by this, right? Now, for example, in general we get a figure which is right at the left hand side bottom of the screen, right? Okay, so we are trying to do what is that R is the region of integration in the xy plane as shown here. Now, for positive f of xy, the definite integral is equal to the volume under the surface z equals to f of xy above the plane xy for x and y in the region R. Now, we write the general notation of double integral as this, where R denotes the region that we are integrating, and which is shown right at the bottom left hand side of the screen with this red and blue marked, right? So this is the region that we are trying to integrate. Just to denote that there is a capital A or small a, doesn't matter. Here I have used a capital A, earlier was a small a. It is just like convention notation, nothing more than that. This portion dA is the tiny chunks of areas dx dy or dy dx, and in the same way dx represents a tiny length in ordinary integral. So this is just to show you that this is the concept that we are building, and this is how from single integral moving to double, and why we use double integral to find out the area under this part. Now, double integrals, as you know, are used anytime when we feel like we want to chop, we want to cut up two-dimensional region into infinitely small areas. This is the notation where again R denotes the region you are integrating, and this is the tiny little chunks which we are cutting out or chopping out in order to make life easy, and we will integrate over it. And this one z equals to f of xy is the two variable function. Now the concept goes something like this, the visualization, that we cut the volume into small pieces, then we find the area by doing an integration, which is the inner integral, that is the inner part, and then we multiply the area each slice by either dx or dy, and then we integrate the infinitesimal small volume to get the volume of the solid as a whole, which is the outer integral. So this is just to give you an idea that how the thought process goes, and how and why we divide these into small pieces and how it goes out. So this is the kind of visualization which will make you understand about those things. Now, when we think of double integral with respect WRT, with respect to tiny areas, it is common to write it in this way, which is a very abstract kind of a notation. And when it comes to so this one, when it comes to compute the integral, we replace this with an actual pair of single integrals, obviously. Now, when we talk of the bounds that can be computed, I mean to say bounded area, which can be a rectangle or eitherwise, right? So R is a rectangle, and these bounds will be constants, and these are denoted in this way. When we are dealing with curved surfaces, when R is curved, right, I mean to say the area which is a really bit curved space, the inner integral are expressed as functions of the outer variable and is denoted by this. So you see that dA is the tiny area and R is chopping it into small pieces, and Z equals to f of xy, or either way these are two variable functions. So I just showed you from single integral we moved into double integral, and the double integral, the real reason for double integral, and moving from bounded or rectangular areas into curved areas, how this changes. Now we come into something which we called surface integral. This is important because, as you have seen, Gauss's law covers up the surface integral part. Now when we talk of surface integral, remember that the concept of surface integral is the same as that of the double integral, right? Now except that, yes, instead of adding up points in a flat two-dimensional space or a region, we are adding up points on a surface, right? We are adding up points on a surface in a space which is curved. Now what we do is that we get this, and then this is the surface S. Now this is the tiny piece of area in S. I have denoted in sigma. Some authors denote sigma, some authors denote A, doesn't matter. So surface integral is more or less same to the surface area, and the double integrals are generally used over flat two-dimensional objects, and surface integral is used over curved two-dimensional objects. So that is the most important thing. Now till now the concept of adding areas into small pieces was confined to flat region, right? Now what if we can use of a curved space? Now in front of you these are two hypothetical cases: the surface of a curved airplane wing with a variable density, and the temperature every point on the curved faces of Earth. This is this hypothetical concept. Now what happens is that the function f, it takes three dimension, which may be density, temperature, air pressure, whatever, but it must take a function in point the three dimension, since points on the surface live in three dimensions. So you see this one I have mentioned is as points in three dimension, and to make life easy I have just shown as an Cartesian coordinates with x, y and z, so that you understand that this is three dimension. This one which you see, this one is the same because the d sigma and d are the same thing. Sigma denotes adding up into discrete space, and A is also the area. So this actually is the surface integral, right? So this gives you a kind of an idea that in case that we are extending our concept from I would say a single dimension to double and then to three dimension, and the functions and the variables changes to x, y and z, how do we use? Don't get confused with the notation of sigma and A. I've used it deliberately so that if you find it in the textbooks you don't get confused. Now this is another kind of an example just to show you that the blue object below is the surface z equals to f of x, y floating above the xy planes. Yes, this is the blue object, and this one is what we are calculating the volume under the surface, z equals to f of x, y, obviously where it is of positive f of xy. So this is kind of a cylinder with a blue area around. So the blue object below is the surface, and this is basically we are calculating the volume under the surface. And more generally it is written as this. This is also an example which I just wanted to show how we are chopping up the rectangular part into small pieces dx and dy, and a circle also chopping up into these pieces. So this is again this one, the R is the region that we are integrating, and these are the small infinitesimal small pieces of dx and dy. So this is a visualization just to tell you that this red circle actually denotes that how we are cutting and chopping the entire area into small dx and dy pieces so that we can calculate the integral, surface integral and so on. So this is the two variable function. Okay, now imagine that this is an area, right? This is the area density. So this is sigma 1, 2 and it goes up to n. And what we are trying to do is that if the surface varies with x and y, what we want to determine is the total mass of the surface. Now we can do this by dividing the surface into two-dimensional segments, which I've already done in the figure. Over each of the area density is approximately constant. Now if we make this area further and further and further smaller, we get the true mass. Now, if dA gets to 0, which I have shown, and n approaches infinity, it is simply that we are adding up the contribution of little pieces of this function, and we are finding this as an area integral of the scalar function. So this is one, and this is how we calculate the mass, which is adding up the pieces up to n. And at the top, I've just given you a formula and just an idea in which we are calculating mass, and this is points to the area integral of the scalar function. Now, when we go further and we understand the concept for flux of a vector field, you know that we have earlier learned about what is a flux of a electric field. Now we will consider flux of a vector field. I will tell you the reason, and you will be surprised and you will be amazed to see how the vector field and the electric field matches with each other. So what is a flux? The flux comes from the Latin word fluxus. It is a jargon, and it tells about a flow of something. So the flux of a vector field, we can imagine as a flow of a vector field through a surface, which is the amount of whatever the vector field represents. It can be a water, fluid, water, anything. So it is a flow which passes through a surface. Now it is difficult to explain, and it is easiest to understand with an example. Now close your eyes. Imagine a river, right? A flowing river with a net strung across it. The river represents a vector field where the vector at a point is the velocity of the water at that point, right? In this example, the flux of the velocity field across the net, the flux of the velocity field across the net is how much total water passes through the net per unit time. Here is a figure right hand side on the top of your screen, which I have tried to show you as the inflow of water which is coming in. Now for a uniform vector field, this one, that is a flux, and a surface which is perpendicular to the direction of the flux, the phi is defined as the product of the field of the magnitude and the area of the surface, which I have taken as a product. In case that it is something where the flux is 0, this one where it is not perpendicular, the flux is 0. And in case if the vector field is uniform but not perpendicular, say it is uniform but not perpendicular to the surface, the flux may be determined by simply finding the component of A, that which I've shown, which is it is a component of A perpendicular to the surface, and then it is that by using the dot product. So E dot, the surface area, and this one is basically the general total overall calculation, or the formula of calculating the flux. So now you see these examples gives you a basic idea, visualization and simple equations in order to find out the flux. But life is not that easy. Now what we have noticed here, or if you see that all these lines, I mean to say that these black lines, the arrows, are all uniform. But in electromagnetism, life is not that easy. Now if you find across this kind of a curved surface where the flux is non-uniform, right, and it goes into the curves up and down in non-uniform area, so here are some flow which is lower, I mean to say lower in rate, and this is the flow which is a little bit higher in the surface. And what we are trying to find out is this: the number of particles per second passing through the surface. Flow, mind it, is different at different places, right? So what we can do is we can in general, we can, if we go for a dimensional analysis, right, then we can just multiply A by the area of the surface, right, if we go by the dimensional analysis. But this is not done. Why? Because we have seen that sometimes the flow is high and sometimes in region flow is low and high, and also it has an angle which I have not mentioned. So what we are trying to find now, we divide, we are not concerned with the speed of the flow and the area of portion of the membrane, but also the component of the flow perpendicular to the surface. So what we do is that on the right hand side, I have shown that I have divided this entire curved surface into small pieces, bits and pieces, which is in blue, and further make it small and small and further small. Now to find the component of A perpendicular to the surface, we find the dot product of A. This is 1, and this is how we do A dot Ni. That means N goes up to I, so that is fine. So what we are doing now, we will take forward this particular figure which we have divided in the next part. So this is the one, right? Now we break into infinitesimal small pieces, and Ni represents the unit normal, F for the segment area dAi, which is quite simple. Now what we see is the flow through the segment, which is the dot product. Now when the segment shrinks to further 0, the summation, that is the discrete part, is this one, which is a second marked in blue box. And now further when we calculate the entire surface into this, and this is what is called the closed surface. So now you can, I hope the concept is quite clear, that we calculated initially the concept of flux through a uniform field. Now we got a non-uniform field where the sometimes the flow is high and flow is low. So we cannot just multiply A with the surface area. We divided into small pieces. We found the flow through the segment. Then we found the flow through the entire surface discretely by using sigma, and then integrating with the closed surface, which is integration, that is the flow through the entire surface. Okay, so we come to here. Now you see the beauty of Gauss's law. So this one is actually what we found, right? And you see on the right, if you see the left hand side of Gauss's law, this part and this part is exactly the same, right? So you can see the beauty. This flow through the entire surface, which we have calculated as A, which is the vector flow, is just similar to the left hand side of the Gauss's equation, and we just have to replace this field, vector field A, with the electricity, and thus we get the Gauss's law. So now you understand the reason that why I started with vector flow. With vector flow, if you can just replace that A arrow with E arrow, which is the electric field, the vector electric field, vector field, then these two parts becomes the same, and that is the beauty of Gauss's law. So we just replace the vector flow and we get the Gauss's law, which is the electric field. Now going further, we just find what is an electric field through a closed surface. Now when we talk of electric field, we get flux, vector field and surface, which is denoted by this. Now we get something which is, if E is uniform and perpendicular to S, we get this formula which is on the top, which is E multiplied by surface area, and we get this one if E is uniform at an angle S, and we get this one if E is non-uniform and at a variable to S. That means non-uniform means what I have shown you, that the surface is sometimes bumpy, the flow is up, so the flow is down, and sometimes it is irregular. So taken this phi E as the flux, E as the vector field, and S as the surface, these are the different formulas in which E is uniform to perpendicular to S, E is uniform at an angle, and E is non-uniform. Now here comes something very important, something easy but very important. This is something very important. Remember that when you employ a physical analogy, right, you are comparing something to something, you are hoping to learn something about the relationships between quantities, not about the quantities themselves. So you can find the electric flux by integrating the normal component of the electric field over the surface. But remember, you should not think of the electric flux as a physical movement of particles. Again, I repeat, you should not think of electric flux as the physical movement of particles, and that is the reason I have written it in bold, that electric flux is not the physical movement of particles. It is an analogy. So the question is that how do we visualize them? So here it is, relationship between quantities, not the quantities themselves. It is between quantities, not the quantities themselves. The question is that how do we visualize them? Now what we do is that we use lines to represent electric fields. Now this one, as you see, these are radially moving out. So we say that this one, yeah, this radially moves out, is the positive flux. Now we get something which is the closed one, which is this, which is moving towards, which is the negative flux. That means it is radially pointing towards it. And then what we get is this one, which is zero flux. That means whatever is getting in, so whatever is getting out, right? So we use lines to represent the electric field. As you can see, you can think of water entering the sink and leaving the sink. So when it is entering the sink, it is negative flux, and when it is leaving the sink, it is a positive flux. Now further what we see is that you see the density of field lines is more. That means the densities are, radially moving out and out and out. So here the density is more. And here what it comes is that the field of density is less. So compared to those things, you can visualize the density is more and less. And coming further, so I can say that field strength is more or less proportional to the density of field lines, right? And this is the general function, that it is more or less equivalent to number of field lines entering the surface. Okay, so we come to field lines are just representation of the electric field. So you see that the electric lines are a little bit less dense here and more dense over here. And here is the flux which I have shown. And this is just to note that field line components parallel to the direction gives a kind of a positive flux. Whereas this particular, the field lines going in and the field lines going in this direction gives a kind of a negative flux. So the strength of the electric field at any point, I would say, is indicated by the spacing of the field line. So you see the spacing on the left hand side, blue is less and it is more at that location. More specifically, the electric field strength can be considered to be proportional of the density of field lines in a plane, which I have shown, and penetrating the surface, and that is exactly what the electric expression of the electric flux gives. So you can just go back and see this is actually what is the equation of the flux. So that's actually shows you a kind of a nice kind of an analogy that you should remember, and this is the way you visualize the flux going in and the flux going out, which gives a kind of a negative flux. Remember one thing, that these are physical analogy. Again, I would repeat, you're learning the relationships between quantities, not about the quantities themselves. So just a quick summary, we learned about double integral, we learned about surface integral, we learned what is called a flux of a vector field and the electric field through a closed surface. So this is quite a kind of a comprehensive and a detailed video. What we will do is that in the next video we will be coming up with what is an enclosed charge and permittivity of free space. More or less that would be covering the final part of the Gauss's integral form. I hope you liked it. Please let me know your comments in the comment section. Do not forget to like, subscribe and share this video, and wish you all a great day ahead. Bye.